start recording. And the first speaker is Alexei Davydov from Ohio. And he will tell us about full center constructions and whatever.
Thank you for such a lovely conference and opportunity to give a talk. Yeah, so I was scheduled at the second slot, and so I thought I'd have an extra hour. So it is all half-baked, but hopefully still somewhat entertaining. And I was also asked to build bridges because it's about conformal field theory and recycling this ancient Indian analogy where sampling something big as an elephant, and I'm an algebraist probably holding the thing detail. But okay, so what do I know about full CFT? I'm bold enough to talk about full CFT state space through this algebraic perspective of full centers. So that is CFT. That is what I have no idea about, but still be talking about at the beginning. And then the full center is algebraic construction, and that's why I feel more or less comfortable. But yeah, what is a CFT? So first, yeah, if you read the Wikipedia article, one of the first sentences is quantum field theory. So quantum field theories come with Hilbert spaces, right? So there is this Hilbert space, which is going to be the full CFT, which is CFT, I think, is like a state space of an infinitely long cylinder. And as a quantum field theory, it's supposed to have operator value distributions on it, whatever it means, called fields, and they can be located on some remaining manifolds in general. But in this two-dimensional case, these are two-dimensional Riemann surfaces, and then they act on the Hilbert. So yeah, Hilbert is assuming unitarity. So here's my first question: what is a non-unitary CFT? I would really like responses from specialists in the audience. They're very few, of course. But if to ignore all these technicalities, we'll still have, like for vectors, we'll still have something like that, and then that can be seen as an action of this field on states. And then there is another sort of important ingredient in the CFT, at least. I'm not sure about quantum field theory in general, but in the CFT, well, the action is supposed to have well-defined limits. So here I'm assuming that I'm on the background where zero makes sense, like a plane or something. And then it gives us a vector in state, so we can assign two fields states. But that assignment, so assignment is supposed to be reversible, right? The name is state field correspondence, and in some sense, this is a subjective thing. So for any state, we have a field as well, and that algebraically says something about like an algebra structure, but with a parameter depending on sitting in the background. So all in all, which is some sort of a algebra object. There's sorry, I didn't mean this. I meant that because yeah, there's a canonical, there's a sort of special vector which is called the vacuum. It's supposed to work for all, but yeah, the state field correspondence. We have to choose one, and why not to choose it given one vacuum? And but practitioners was probably, and we saw it in all the sort of most of the talks from last week. The sort of practical side of the CFT is this collection of correlators, which again is supposed to use the inner product of this Hilbert space. So what to do in non-unitary one, and then so collection of fields positioned at some points, give right, and then a pair of vectors, but we can always assume I think that to be the vacuum, and that is, as I understand, is abbreviated to these things, and then again, they're supposed to be real value functions defined without mononomials, so properly defined analytic. And that's what people can compute using different methods, and that's what really is sort of visible from. Am I right? Am I wrong? Am I completely wrong? Am I slightly wrong? No one's saying anything. So people are polite. Maybe I'm completely. Okay. So
so this of x, you want to think of it as a distribution in x, maybe?
yes. So yeah, it's a
really function.
yeah. It's not a function. It's yeah. So as I said, it's a greater value distribution, whatever it means. So yeah, it's sort of very shaky concept in the first place. Yes. But these are functions. So somehow the sort of the secret ingredient of a quantum field, that although these objects are very poorly defined, these are almost like physical quantities. If we take the squares, then they will be physical quantities. Computing probabilities of some real physical processes, and that's what really physicists are interested in, as I imagine. But this gadget allows to compute the things. So yeah, what else do we have in that is all more or less true for any quantum field theory, right? But what conformal brings in? So the conformals, sorry, conformal means that yeah, this two-dimensional manifold, this Riemann surface, really comes equipped with now comes equipped with complete structure, and then we could see the behavior of these fields with respect to complex structures, and then so M now is M is really two-dimensional thing, and now it's a complex curve. Complex 2D complex plus Riemann with the compatibility, and then we could talk about fields which depends only holomorphically or anti-holomorphically on their positions, and then inside this state space, which is actually also because of the state field correspondence is a field space, we could single out fields which are like that, so holomorphic and anti-holomorphic, and they will be. Oh yeah, I forgot to say that. Yeah, this in terms of fields, we could use these functions to define something like a multiplication of the fields, operator product expansion. It will not be completely defined. It will be having poles when positions coincide, but otherwise it will be always defined. And then, yeah, and then the feature of this complex structure is that we are allowed to single out these two things, and then they will be closed under the product expansions, and that's what so part of the participants are really working in. So the mathematical formalization is comes out with the name of vertex algebras, but they're not just vertex algebras because of the conformal symmetry. So these correlators are supposed to be conformally invariant, and then because of this really strong condition, we also have inside this holomorphic and anti-holomorphic subalgebras, we have Virasoro. So in physics, it comes as usually as a energy momentum tensor, such. And so this vertex algebras are really, again, vertex algebras are probably true for all quantum story, but quantum field theory story, but these are vertex separate algebras, which is much more rigid thing. So they are vertex algebras containing Virasoro vector, and then the again action traditionally in most of my story will be about rational case, which is purely understood algebraically, and there the action of the L node of the zero mode of this is going to be diagonalizable. But that is one of the, I think, topics of this meeting is what to do if it is not. But nevertheless. So yeah, just again, I'm an algebraist and I'm only seeing a very blurry picture. My vision is really not so good, and I've not seeing so many details, and it would be lovely if someone will be interrupted and saying, okay, now it's to be corrected. But so far, no one is interrupting, and yeah, and then perhaps another sort of, yeah, okay, please correct me about history. So in my understanding, historically, again, rational was sort of the easiest case, as the easiest case were first to analyze, and by people from two different physical origins, string theorists, high-energy physicists, and statistical mechanic people, lattice models. They all ended up with exactly the same structure. In string theory, it is a world sheet part of the string. In lattice theories, it is limits, which give conformal invariant theories. And so in both the kind of the easiest quantities which you can extract are, yeah, if you take this L0 mode and then compute the trace, which again is supposed to exist, the trace of this of the two combined in the following way. So yeah, when you see, so why Virasoro? Because when you separate, that is not true, the first instance of holomorphic factorization, then the it is possible to have a central extension. So taking the square root, it is possible to have a central extension, and the Witt algebra of the infinitesimal two-dimensional symmetries extends centrally. And there's only one interesting central extension, the Virasoro. So that this so the central charge, this anomaly is the C. And then we have two coming from holomorphic, anti-holomorphic. So if we compute, that's supposed to make sense. And if we compute it, it is, in rational at least case, it is something nice. It factorizes into a sum of holomorphic, anti-holomorphic terms. So that's called the modular invariant, because really that is like tracing around the cylinder. And if you expand Q in the usual way and then look at the tau, tau will be modular parameter in the modular space of tori, complex structures of torus. And then, yeah, surprise, surprise, this modular invariant thing. And as traditional already by now, the only example will be coming from it. And yeah, this partition function is called easing is if I'm not mistaken, is literally can be written in terms of either the candidate function and Bernoulli theta functions like that. But so if holomorphic anti-holomorphic factorization is somewhat different. So yeah, 3 terms. And when and these things really are holomorphic functions, and even better, so looked at as a series, as a formal series, they have non-negative integer coefficients. So, but then people realize that they're just really characters of some representations of really these VOAs. So the whole story, as I understand, is here, like Milan Polikov and Zamolochikov's paper was really analyzing these interesting behaviors. Okay, please. So this example is the first non-trivial example of something called rational conformal field theory. And in this case, conformal field theory is rational if H considered as a module of a product of left and right vertex operator subalgebras is semi-simple. Meaning that it's just a direct sum of finitely many pieces. And then that's what really gives this holomorphic factorization of the partition function, that there are 3 irreducible pieces inside this considered as a module. And yeah, in this case, the properly defined representations of this vertex operator algebras form semi-simple categories. But they're not just semi-simple. These correlation functions allow to equip them with a very rich structure of a modular category. And what is modular was defined many times, but maybe briefly recalling just the ingredients. It is monoidal, while being semi-simple, it is also monoidal. And rigid. And that seems to be like the biggest work in constructing duals. But it is done, and then it is braided, coming from effectively locality of quantum field theory of product expansions, and then it is also ribbon And the ribbon structure, this technically comes from the basically Virasoro action from the L0 eigenvalues. So the lowest or the highest L0 eigenvalue exponentiated is what gives the structure of ribbon category on the category representations. And sorry, yes, please.
Can you just remember me rigid? What is
rigid? Yeah. So rigid means that any object has a dual. And the two versions in the monoidal setting, it would look at left and right, but because of the braided, they're sort of the same, but it's actually ribbon, which really links them tightly together. So,
sorry. So you complained about non-unitary CFT, but all these properties are that true in non-unitary minimal models as well.
Exactly. So they're here. But yeah, how to make sense of the correlators? It's supposed to be using Hermitian scalar product. How to do it without scalar products? If you know like accounts where I can read about it, I can educate myself. Please let me know. But it's kind of usually QFT assumes to be unitary, so unitarity and locality are things.
Just need to be non-degenerate. It can be.
It doesn't have to be positively definite.
Symplectic fermions, everything is fine, right? It's not.
So you still have the.
It's not degenerate form. It's not positive definite.
Easy fix. Yeah, just drop.
It's a crane space. It's a crane space. There is a.
So it's not. Yeah. Okay. I didn't say it's Hilbert space, but it's just it's a state space. So what are they called? Vector space with no degenerate.
Like in many cases, they even crane spaces. You know this crane space.
A lucid.
But no.
It should be the.
Pairing, which is this. Okay, thank you. Yeah, so there are minimal models there. Easiest things one can construct, which cannot be made unitary as a category. So if it is, unitarity can be seen on the level of categories. So there's a notion of unitary is a unitary version of all that, where morphisms have this Hermitian products. Morphism spaces are finite dimensional because this is semi-simple, finite, meaning that there's only finitely many simple objects. And the home spaces are also finite dimensional. So the category is just a collection of vector spaces. How hard can it be? But the hardness is in this monoidal structure, and then the braiding is easier, but monoidal is really sort of hard describing by hand. The so-called 6J symbols one has to deal with, describing the associativity constraint, and they're really hard to solve for. The equation is very non-linear unless it is a pointed case. But last condition is non-degeneracy. And that is a very crucial condition. And from algebraic point of view, this condition is sort of very natural in a sense. So if we have braided, that is a categorical version of being commutative. But on these two levels, which we have in categories, we already can see the distinction between E2 and E infinity. So En is in topological sense is a measure of how commutative topological multiplication can be, and it is modeled by the sort of braiding behavior of disks and dimensional disks inside the disk. And braiding is E2, and then we can have a stronger version, symmetry. So braiding usually denoted like that traditionally. In the string diagrammatic language, whatever it means. So the symmetric is is a special case of that, and that is usually the sort of the classical representation theory, where tensor product is a tensor product of vector spaces, and the symmetry is just a swap, and the symmetry done twice doesn't do anything, and so the braids become transparent. We can pull strings through each other. And the non-degeneracy is a condition that there's only sort of one up to multiple transparent object in the whole category, and that is the monoidal unit of this identity, which sort of is assumed to be here. And yeah, my question again to the specialists: what is the reason for that, or what is the counterpart of how non-degeneracy can be seen in the VOE? When we generalize from rational to non-rational, so presumably this is still a good condition to keep. But what is this?
It depends on the category of modules you take, right? So there is a reasonable class of categories of modules. It's non-degenerate. I mean, for Virasoro, non-semi-simple Virasoro, right? I can give you category of modules. It's like Cardanoistic category. It has big Migrer center.
At the real affinity, right? Yeah. Real affinity.
Yeah. So it's not always.
So
it's
really just selecting
selecting this,
selecting good things. Just kind of artificial.
No, for C2 confined, I think it can be made precise. Robert McRae had a result about this.
Okay.
Reasonable class of modules. If it's rigid, it's not the
Maybe he's going to watch sometime later and then will come with the solution. So yeah, what non-degeneracy? Non-degeneracy just appears to be here in all the rational examples.
But do you really need this this bilinear product? Like to compute your partition function, you just take a trace, right? You don't need a product.
The product of the representations.
Yeah, the bilinear product on the
on the state space. But no, but yeah, so what is then? What are then correlators?
Well, your partition function is an example of correlator which you computed without using this product.
Yeah, that's right. So it can be written just as a trace, and then hoping for the best that it makes sense. But in general, I need correlators like to define. To define multiplicities for tensor products, right? So, but what are they? I'm an algebraist, so algebraists are brought up like that. So it should be definition, theorem, example, life cycle of an algebraist or mathematician, maybe in generals. And then without definition, I really feel.
Also, it's not just trace, it's graded trace. Trace is not defined on infinite dimensional vector space. You need
it's a graded trace. Yeah, it's a graded trace. It's a graded trace. Because again, of this assumption that L0 acts nicely, that eigenspace, generalized eigenspaces are finite dimensional, and that makes sense.
No, but the point is that you can compute these directly, even for endpoint functions, even for iteratively using Jou reduction for any VOA.
So you said can or cannot?
Can.
Cannot.
Can.
Can. Yeah, that's right. So they're there. They're the gist of it, as I understand. They're the physical, the interesting quantities, and then everything comes from them. But what do we need to have to like build it back? Because I'm an algebraist now, and I see very well, very much processed results from analysis of rational conformal field theories, which is a pair of nice categories. Well, maybe some dirty algebra proceeding behind them, but for an algebraist, they're just a pair of this modular modular fusion categories, and something in their product, right? Because for rational, it was known from the beginning. We have this factorization. And for semi-simple, yeah, still called D-line, but that is just a very simple sort of linear product of semi-simple linear categories, at least in algebraically closed way. And then we have this object. I'll call it the same. I'll denote it the same way as partition function, and it is, yeah, sort of categorical qualification of this module anyway. And what are the properties again coming from operator, product expansion, and the properties of it is that it is an algebra object. And makes sense because these are monodal categories. We could talk about algebras inside, but it's not just a random algebra. It is, yeah, many things. It's commutative. Make sense of that in a braided category. With operator, we could say that multiplication is commutative. So yeah, my diagrams go to bottom. I'm sort of a pessimist in that sense, and then the commutativity will be this diagram. That is the multiplication map. The strings are all labeled by the same object. That algebra thing. And on top of that, it is Riemann. There's just absence of anomaly. There's the twist, which measures the conformal weight, is all the same for left and right components, or just identity for this. And am I missing something? No, I'm missing that it is connected. I like the adjective invented by Fuchs, Runkel and Schweigert, haploid, but connected seems to be probably. Meaning again that the identity object of this category sits so the home space of the identity, which is just the product of two identities. One dimensional. So only the unit morphism, nothing else. Scales only. Again, where does it come from in VOAs? Connectedness. Is it that the conformal weight zero component one dimensional? Is it this CFT condition, CFT type condition?
But commutativity comes, right? Commutativity.
Sorry?
Commutativity is from CFT action should come, right?
Commutativity is from locality. No, but this connectedness.
Yeah.
Is it just the same as to say that, yeah, the
process all the, yeah. So that's something we have to compare of that.
This next question there. So is it related to saying that left-right things are one-dimensional in degree zero, conformal weight zero, or maybe no? But yeah, it's also separable, which is a categorical right version of semi-simplicity. And finally, but not least, it is, it's called Lagrangian. And that is a very strong condition. So I'll have to explain it quickly. Algebraically, again, it's a very nice story. So imagine that we have a commutative algebra, a thing like that in the braided category. So what we call it, say, algebra. And yeah, it was first analyzed by an algebraist without any motivation, as I understand, as I know. Well, the Paragas was just investigating this algebraic question. So you could still look at the category of modules. Inside this braided category, and then it comes with a another product. If the category is good enough, if you have co-equalizers, if you can make sense of quotient, sort of, you can make the sense of this balanced product, or relative product with respect to A. You can tensor in the category, but then you take two modules and you want to make it a module again, and would like equalize the action on the first and on the second. As usual in algebra, when we take modules over equative algebra, and then you have this well defined as this quotient. Yeah, if it is semi-simple, no problem at all. The problem is that it's not going to be braided, because yeah, how would you like it to make it braided? You just use the braiding of the original categories. What else do you have? And it's not. So this is not braided in general. But for the found fix, you could look at special modules. He called them dyslexic, and I can relate. I'm not dyslexic. But now, again, after Fuchs, Runkel and Schweigert, they're called local. And I think that's a much better name, because really that is a manifestation of locality from quantum field theory, which will be braided. With respect, with the same braiding coming from the category. And then what is locality is just, yeah, what makes it not braided in the first place? It's the strings winding one around the other. And so if you just remedy it, so this time it is a module string, and this is a module action, and then you want it to be not quite transparent, but transparent when you act. And if you have this condition, then you call module local, or they call them dyslectic, and then they form the largest braided subcategory of this with that braided curve from C. So Lagrangian means that, yeah, and then Lagrangian means that, okay, let's call them C and D. Lagrangian means that if we look at this local things, we won't see anything interesting. We just see the algebra as a module of itself and nothing else. So the algebra of the module of itself will always be an example of a local module, but that will be the sort of unit object with respect to this tensor product. Not so interesting. So it will be just multiples of that in general. In a semi-simple case, it will be just the category of vector spaces. And that is happens for all rational conformal field theories, the full state spaces considered as an object in here. And can be questioned, where does it come from? In terms of perhaps operator product expansions, that is some sort of locality, yeah, in what sense? Because you're supposed to look at modules over chiral halves, and those are not really necessarily present even inside the full state space, but you still want to be local with all of them. So what is the quantum field theory way of saying it? Locality is really just a feature of quantum field theory. All these questions came to me like yesterday, and I was prepared for the talk. And, why? But it is here. And that's what really constrains the story very much, rational story very much. So let me see. So how much time?
20 minutes.
Ooh. I'm not going to talk about full sentences. So again, some algebra. So we have this product of categories, modular tensor category, modular fusion categories. And we happen to have this Lagrangian algebra. What can we say about that? And it seems you can say almost everything. So first we can, using this algebra object, we could look at sort of maximal algebras in each of them. Maybe I will call it C left and C right. Minimax right. So the maximal such that yeah. Now we have to fix the order.
So you define centers?
Hmm?
You want to define centers? ZL.
No, I'm just talking stuff. I'm not defining anything yet. I'm analyzing what is to have such a Lagrangian algebra object in a product of two categories. That is a situation which is rational conformal field theories. So you can always define this. They will be commutative. Well, they will be commutative. There will be again ribbon. They will be connected. They will be separable. It is sort of abbreviated under etal or maybe ribbon etal. And then, again, using this language of local modules, very convenient for this story, the sort of the rest of the module invariant can be organized into a braided monoidal equivalence between, so we take, say, left, and we take local modules in the left sector, and then it is the right sector, local modules, but we have to reverse the braid. It's really ribbon in this case, ribbon equivalence. So if assuming that these are trivial, this is just one, then modular invariant object would be something which is called permutation modular invariant, when you just have the blocks grouped without any sum. And in general, if we are starting from category theory, we don't have to have permutation modular invariants. We have this, they were called in rational conformal field theory type 1 parents. And then upon extending, we do have permutation variant. But here's the first statement, which is obvious, but I never saw it in the expositions on rational conformal field theory, that in rational conformal field theory, this left and right are either categorical. The representation categories will have to be the same. Well, I forgot to say, I erased it all, it was here, but yeah, there's an extra condition of canceling the global anomaly that the central charges of the left and right are the same. Of two vertex separate algebras are the same. Now we have another condition that representation categories are just equivalent. So that's my theorem. It's not much of a proof, but it's a ground statement. So yeah, representations in rational VOA, if you look at the left and right movers in Minkowski, but in Euclidean it's just holomorphic and anti-holomorphic sectors, their representation categories have to be equivalent. Why? The one missing ingredient, apart from this categorical analysis, is the relation between local modules and VOAs. So let's just look at this local module situation. And so here V is a VOA. But let's call it rational, so that the representation category is modular tensor category, modular fusion category. And then we have a commutative algebra object in that. And the commutative algebra is this etal, again, meaning that it is connected and separable. So there is a unpacking of that in the case when the representations of POA that was done by Juan Kirillov and Lipovsky, and then I think the ribbon part of it was added later by Krotik, and then there was a generalization again done by him, which might be helpful for non-rational case. But yeah, what is this? Yes, this I think it was mentioned before. It corresponds in one-to-one way to chiral extensions. So this, as a representation, is VOA itself. The algebra structure is really, if you think in terms of the intertwiners, this is a vertex operator structure on this representation. And commutativity is nothing but locality, so it is V or A, because again it contains the trivial one as any algebra, and then it is a chiral extension. So what's called chiral extension. Moreover, if we look at, and it's still going to be rational, because if we look at its representation category, we can see it in these algebraic terms very easily, nothing but category of local modules. On the back, what do we have? So we have these two algebras, which are Ital algebras on left.
Can you say again what you mean by ribbon Ital?
So Ital is if we have just this is called Ital. Ribbon is here. That the ribbon twist is identical. So ribbon is actually can be decoupled. It's not. Ital and Lagrangian is definable without specifying a good structure. And then yeah, what do we have? From a modular invariant, from just the sheer existence of it, that the left and right sectors. Yeah, if we look at it, and if we happen to have these things, they have to be trivial, because if they are not, we didn't collect all the holomorphic and all the anti-holomorphic things in the first round. Because if they are not, we have this this way of extending left and right holomorphic and homomorphic algebras, which means that we did do a poor job in the first place. So the these parents different monoidal units, and as a result, the local modules are just the categories, and the proof is done. Yes, as I said, it's not going to be too long.
Repeat again.
The claim is, in view of the HKL theorem, that the left and the right parents of the modular environment coming from conformal field theory, rational conformal field theory, have to be trivial, because if they are not, then we have chiral extensions of them coming from this modular invariant. But the chiral extension will still be holomorphic and anti-holomorphic.
So Z will be extension, right?
Yeah. So that L will be extensions of yeah. So that Z sub L will be an algebra object in.
Z will be algebra object in ZL.
So that L, yeah, will be an algebra object in the representations of. Yeah, I'm now specifying the general story. Yeah, there will be algebra object in the representations of left-right movers, and if you look at the OPs, they will still be holomorphic, anti-holomorphic. So that will be meaning that we didn't collect them all. Because how do we define them? We take all which depend holomorphically and all which depend anti-holomorphically. And if we do that in the modular invariant, they should appear with multiplicity. There should be no parents. And so the at least in the view of a full state space, rational conformal field theory, algebraically is given now by a pair of vertex separate algebras, left, right, so as well. Some rational VOAs with the same central charge. Plus categorical data of this permutation module invariant, plus the manifestation of them being equicategorical. So each choice, a concrete choice coming from the module invariant. So the F, which is just the equivalence between the categories of representations.
So you argue that L should be tensor unit, and then F gives you equivalence, right?
Yes.
If you apply to tensor unit.
Yes. So
Because every local module will
yeah,
be...
if these two are, yeah. So by this extension, you can sort of still leave this module invariant to the case to this left and right, the product of these two, and then it effectively making this left and right parents trivial, and then you could see that just the graph, yeah. You look at the graph of this object, and it is the graph of an equivalence, and using the conditions on that object, you see that this equivalence is braided, is monoidal, braided, and ribbon, all that.
Yes, you said if they are trivial, then invariants will
Permutation invariants, yeah.
So you say they're all permutation invariants.
So in the CFT, you only have permutation module invariance. If you don't, it means that you are really constructing your theory. So let me give an example. Yeah, it still makes sense when you construct the theory. So start like with two nice VOAs, like a phi at an integer level, and you know the representation categories, and you could analyze categorically which two can be glued together. So you still have to impose this central charge condition for the conformal field theory construction, but categorically, instead of analyzing for module invariance, it's just a pure algebra. And then, so one example, but yeah, really, for an example, you could take something like 8 copies of A1 level 1, and then G2 level 1, and F4 level 1. So they can be glued together. They can have the same central charge.
I mean, one is a chiral extension of the other.
No, they're not.
Glued together. I mean, the
VOAs can be made left and right. So the VOAs, these are VOAs. They can be thought of as the left and right sectors of a rational conformal field theory. But the way you glue it, the module invariance will be stupid. Like you just have one summand in the sum expansion in the holomorphic factorization. So they can be glued. So that can be F. It's not like really. I cannot write it as VL and VR, because VL and VR for both will be, what will it be? It will be E8. So in only way you can glue them, when you analyze it, when you just look at left and right movers, they will be E8. There will be the chiral extensions of the both. There's a more interesting example when the left and right are not the same. It's still kind of like this silly type of example. So it's something like D12 level 2.
Sorry, I didn't get your notation. So what do you mean by A8, 1, 1 again?
8 copies.
8
copies. The product of 8 copies of this tensor product of VOAs makes sense. You can tensor
1, 1. What is your notation? 1, 1.
A1 is a Dynkin notation of mine.
Yes, and
level
second one is a level or what?
Level.
Okay, because you did the trace notations.
Yeah, this is conformal, rational conformal field theory notations.
I mean,
and then if it's a B12 at level 2, and we take what say A6 at level 1, but take 4 times, it still can be glued. Again,
But
the same.
still even first example.
Yes.
Not too fast. When you say it's sub VOA in VL. Okay, there is one.
They both are conformal.
Both?
Both are conformal embedded.
Two conformal embeddings into V8. Okay.
And then the only way of putting modular invariants on their product in the finding the only modular invariant in their product is this one.
Because it's not to be holomorphic or what?
Yeah. So the
Holomorphic.
it will really be a holomorphic theory. It will be
Okay.
meromorphic theory with 2 sectors be holomorphic. So nothing else. Yeah. Nothing else can be done if you want them to be inside left and right loops.
But the categories are equivalent or
No.
no?
No, but again, that's an artifact of our construction because we like affine. We start with them. Well, this is also affine, but in this example, the left and right movers will not be affine, but will still be holomorphic. And will be non-isomorphic as vertex separator algebras, but will still be holomorphic and will still have meromorphic theory. If we that has this are coming as conformal weight 1 things. That's why we like them, because again, analyzing theory is giving us that. But then note the full things. Full things are this simple current extensions, maximal simple current extensions. I need to speed up.
We can. I don't know. I'm fine if you continue tomorrow in the morning. We have a free slot. But
No, I don't have. I might talk about
you
something
started,
else,
right?
if you
You
like, but I don't have that much. I just have some propose. Yeah, I need to talk about full sensor, but I don't have that much. So yeah, there's something which I thought about. If we have this rational conformal theories, we have this expression. This expression can be like mirrored. That is just quasi-inverse, just formally. But it's not just formal mirror operation. It looks like we could do it with any conformal field theory. We can say that we are universally changing complex structure to the negative complex structure. And then the conformal field theory will giving us correlators, and then they still give us correlators, but now we sort of secretly changed all conformal structure on all Riemann surfaces to the negative version. And that will be what would give this in a rational case. So this operation of reversing conformal field theory makes sense in general, and not just for conformal, at least. Yeah, maybe for quantum field theories, but this for topological it makes sense. But there we just reverse orientation on the background, and then the tensor product together with this will give us a group structure if we look at rational conformal field theory, if we look at conformal field theories, modulo those which can have boundary. So well, okay. So that is the topic of my talk. So the full center is really about boundarable case. But what is to have boundary for a rational, at least a rational conformal field theory. I don't have much time, like a few minutes, right? So I'll have to be quick. And it it requires that the left and right movers are the same. Right, so existence of boundary conditions will require that left and right movers are the same. And after that, everything works. So, but yeah, I'm skipping a lot of history. But yeah, first it requires that.
What do you mean isomorphic, that one is the reverse of the other?
Yeah. Isomorphic, but yeah, inside the given one, they're really the same. And then, so presumably there might be interesting ways of still gluing them, but no, that is so-called boundary bulk correspondence, which says that it doesn't matter how we glue them. So this third component plays no role. If FL and FR are the same, doesn't matter if these are the same, doesn't matter what this component is, we will always have the boundary, well-defined boundary. So algebraically, it is framed in terms of the module category. You could look at boundary conditions. So the simple boundary conditions, you could make sense of them as objects, and it will become semi-simple category. And then I'm sort of referring to this picture of a cylinder, but now it is not infinite. Now we could put boundary conditions and then put boundary conditions on both ends of the cylinder. So make a final cylinder from both ends, and then we look at these spaces as and then naturally modules over left-right movers. Let's fix it to be left. So they are these state spaces with fixed boundary conditions are modules, and algebraically what it means is that we are really having a module category, and these guys are action homes for objects A and B. And so we can make a category and we can make an action out of all this data. So that is like starting with the work of Cardi. I think Cardi was the first. And yeah, and then the boundary bulk correspondence is an algebraic statement that if you look at the module category of MTC, so semi-simple, simple as a module, but semi-simple as a category. And C is MFC. Then you could make a module invariant out of it, so you could reconstruct the bulk module invariant, and then you could make any module invariant in the bulk. So the bulk will be the module invariant is this full center, an object this time in the product of the left and the right, which is the same, but sort of holomorphically mirrored. And then any comes this way. So any module invariant will have some B, at least in Russian conformal case. And that is independently by Kohn and Runkel, or maybe Fjellstad, Fuchs, Runkel and Schweigert first, but then Kohn and Runkel will like all the final nails into that, and then independently Ettinghoff, Nikšić, and Ostrich, they were just algebraically proving this fact. And so yeah, the boundary extension requires just that. And then yeah, the group of yeah, but okay, here's a slogan in general, rational or not. So there's a smear version of a CFT. And then if you take the original and the mirror version together, it will be boundarable. So that is the statement that that modular boundary conformal field theories you will have to. Rational in particular, rational will be somewhat boring, so it will be just still like this data modular diagonal. But yeah, in topological field theories in 3 dimensions, it still makes sense, and that gives us beat group. So maybe in quantum field theories it might be something interesting as well. Oh yeah, but yeah, beyond rational. So what is this full center? I only have like 10 minutes left. I don't.
Yeah, no time left.
I don't have enough.
We continue
for the full
tomorrow
talk.
morning.
I don't have enough for the full talk. I only have like 10 minutes left of what is this full center categorically. You see, just it makes a perfect sense. So I only have like maybe 15 minutes more. If you want me to talk.
Can you talk tomorrow for half an hour? We can make start at 10:30. Why should we run?
Okay.
Maybe you can recap a bit because some examples were fast.
Okay.
I'm sure you will make it even for 1 hour.
No,
You think it's slow? You think you have
no, that
nothing,
would
but
be push.
in the end. So should we continue tomorrow at 10:30? Yeah. Otherwise, we. Okay, let's thank Alyosha. Any questions?
Everything was clear.
I have one question still. I don't. So from your examples, if it's not boundarable, you say category should be equivalent, but you have examples when VOAs are not the same.
Yeah. Yeah. So like here, these two areas are not the same. These are taken from the Schweigert list. It's a central chest 24. But yeah, they're both holomorphic, so the representation categories are very boring, just vector spaces. But VOAs are different because conformal weight 1 components are these two.
Yes.
But if you put them together in the CFT, you have to extend them. Because how else do you see the left and the right holomorphic sectors? And then
you get interesting modular invariant.
In the stupid modular invariant upon extension, you just glue two holomorphic sectors together with a modular invariant 1. So it's vect on both sides. There's only one modular invariant, which is just the 1.
Are there examples which give you non-trivial invariant?
Yeah, permutations. Yeah, if you have like a symmetry of a VOA, you could always make this the same on the right, and then you have permutation. Yeah, in general, we have many VOAs with the same representation categories. So very thin shadow of a VOA. Then if it is the same, examples.
So what are examples outside of holomorphic which have same representations?
And the same central charge.
And the same central charge, yeah.
I have to prepare. Okay, I have to prepare. Yeah. What is the smallest? Yeah, I have to prepare.
Tomorrow. Okay.
Tomorrow. Oh, is it tomorrow?
Tomorrow we have a free slot, right? Because Lucas Wacky slot was moved to previous week. So we have one free slot morning tomorrow. But like we can start maybe like at 10:30 if you say you need half an hour, or 10:15 say. What do you think? Let's start 10:15 tomorrow. You just go slow and cool.
So I am okay.
Okay. No more questions? No more questions? Okay. Thank you, Alyosha. Okay, we'll meet 11:30. Now it's coffee break. Second speaker is Robert.